is a calibration data set. What I want to do with that is to put that into a regression program and show you what sorts of things can be done based on that regression analysis. So here is that data set prepared for use by the JUMP statistical program. And regression analysis in JUMP, at least simple linear regression analysis, is done by using this fit y by x facility in JUMP. My response is what I've called little y. My factor is what I've called little x. And if I tell JUMP to go, it takes that data set and produces this picture. Now it's a pretty straight line picture, as one would hope and one would expect, and it's only these 2 points here where I got different values of y for a given x input. In order to get JUMP to give me a complete regression report, what I need to do is come over here and tell it to fit a line. By telling it to fit a line, I get this report, and what I want to do now is to talk about some things that I can learn from this JUMP report and make inferences for this caliper. In the first place, there is on this JUMP report a quote-unquote root mean squared error up here in this summary of fit, and that number is 0.031453. That, by the way, is the square root of this number down here, which is the mean square error. This is my estimate of sigma. So if I go back to a place where I can write here and talk about the caliper data, this S for line fitting is this number 0.031453, and that has the units of the readout, and so that's in millimeters. Okay. One thing I can do with that is to make confidence limits for the repeatability standard deviation. So, and then for example, confidence limits for sigma, okay, which is really a repeatability standard deviation, are, well, I can take this 0.031453 and I can hedge it. I'll hedge it by square root of a chi-square value, degrees of freedom square root of degrees of freedom over a chi-square value. Degrees of freedom, well, there were 20 data points involved, 20 data pairs, and that means that number of data points minus 2 is going to be 18. So I'm going to put 18 both places. And then if I want, say, 95% confidence, I'll have to look in a chi-square table for 18 degrees of freedom. So let's make these 95% limits, and 18 degrees of freedom, the upper 2.5% point is 31.526, and the lower 2.5% point is 8.321, and you can do the arithmetic there at home. These are in units of millimeters. So if one were to ask the question, how repeatable is this digital caliper, those are reasonable limits to use to describe that. Now, another thing that I can draw from this regression analysis is to come here and look at this equation that says how I think average y is related to x, and I can think about perhaps using this equation if at some later point I read out some value of y coming over to this line and dropping down and seeing what the corresponding value of x would be. Okay, so another thing that I can do with this analysis is basically to invent this conversion equation. So I can use the least squares line to develop a sensible conversion from y to x. And the way that I would do that is simply take the equation that says that y is minus 0.0917, say, plus 25.599x, and think about solving that for x in terms of y. So this implies that x then would be y plus 0.0917 divided by 25.599. Okay, so I said that calibration was about measuring knowns, making measurements on known measurands, and if necessary finding a way to convert back from one to another. And even though I'm now working here in two different units, x is in units of inches and y is in units of millimeters, here's a way to go from y to x's. So you might call that, if you wanted to, you might call it a calibration equation. So, for example, if I read, say, 4.0 from the caliper, okay, I might then say that X, okay, this is 4.0 millimeters, I might say X is 4.0 plus this 0.091708 divided by 25.599. Okay, so that's the way I'm thinking about using this conversion equation. Even better, it turns out that I can use prediction limits somehow in reverse to get a confidence interval for for X given a future red value of Y. Okay, so what I'm thinking about doing is this. Here is this jump report, and I'm going to grab the corner of this picture and enlarge it somewhat so that I can do some things with it. And if I go down here to that little red triangle next to linear fit, I can put on this plot what Jump calls confidence limits for individuals. I really don't like that name. They're prediction limits for individuals, but that, as it turns out, is what Jump calls it. So there are the prediction limits for a given value, for a value of Y at a particular value of X. So if you put in this value of X, there's the value on the least squares line, and those two dotted lines above and below delineate what 95% prediction limits for a new value of Y at that given X would be. What's really slick is that it turns out that I can run this thinking backwards and take a value of Y, say Y of 4.0, and come over here and read down to X what the corresponding 95% confidence limits would be for X if I have a red value of Y equal to that. Jump is really slick. I can use the so-called crosshair tool in Jump to do this very, very accurately. So if I go over there, I click on the crosshair tool, I line myself up at 4.0 vertically. I can read off 0.156 horizontally, and I can read off about 163 horizontally. So my point is that for example, if I read y of 4.0 in the future, 95% confidence limits for x are 0.1, I've already forgotten, and 0.163, I think this is 0.154, and those are in terms of inches. Let me just check that. If I put this back up here, I guess it was 0.157, about 0.163, so it's not 0.154 but 0.157 inches, and turns out that's a perfectly legitimate statistical method, is to take those prediction limits and invert them to make confidence limits for x given a particular red value of y. There's one other thing that I want to then think about in this context, and that is that the fact that I can use confidence limits for the slope of this linear regression model to investigate the quote-unquote linearity, linearity constancy of bias of the device. Okay, when x and y are in the same units, this is just a matter of checking to see whether the confidence limits for the slope include the value or confidence limits, the confidence interval for beta 1 includes the number 1.0. If it does, that says that average y changes 1 unit for every increase of 1 unit in x, and you've got a constant constant bias. You've got linearity of the caliper. In the present case, here in this example, knowing that 1 inch equals 25.4 millimeters, what I want to do is check whether this slope is 25.4. Okay, And if I go back to this jump printout now and look in this parameter estimates table, there is an X line that says the least squares slope is 25.599, and there is its standard error. To 3 decimal places, it's 0.222. So the point here is that from the printout, or from the jump report, beta 1 is this number 25.599, sorry, B1, the estimate of beta 1 is 25.599, and the standard error for B1 is 0.222, and so 95% confidence limits for beta 1 are going to be 25.599 plus or minus a t-value times 0.222, and the t-value is going to be 2.093, and what is that? That's the upper 2.5% point of T with degrees of freedom, sample size, number of data points minus 2, that's 18, okay, and that is 0.047. And the point here is that if I take those limits of 2.599 plus or minus 0.047, these do not include 25.4, and what that suggests is that that slope on the relationship between X and Y is not exactly 25.4, and that suggests that the device does not have a constant bias. So the calipers do not appear to be quite linear in the sense of having a constant bias. The point of this discussion has been that regression analysis, in particular simple linear regression analysis, is a very useful tool in calibration. Calibration is a very important activity. If I'm going to have accurate measurements, then I need to know that my measurement devices are well calibrated. That may involve having to invent a conversion between what is measured, Y, and what should be treated as a measurement, a measurement X, and I may very well need to get that by doing one of these deals that I've done here in this example of taking a least squares line and solving the equation of the least squares line for X as a function of Y, and treating that as a conversion scheme. That's what I want to say about the topic of calibration and regression analysis. Next up, I'll say a bit about gauge R and R